Okay, this is chapter 10.4, Inscribed Angles and Polygons. So the essential question is, how are inscribed angles related to their intercepted arcs? How are the angles of an inscribed quadrilateral, four-sided figure, related to each other? So an inscribed angle is an angle whose vertex is on the circle. So let me just highlight that. Q is right here. Its vertex is on the circle. Okay, and whose sides contain chords of the circle. So this blue line here, PQ and RQ, are chords because their endpoints are both on the circle. So that is an inscribed angle, an angle whose vertex is on the circle and whose sides contain chords in the circle. An arc that lies between two lines, rays, or segments is called an intercepted arc. So angle PQR is the inscribed angle. And right there, let me do that with a smaller. The intercepted arc is right here. Okay, the arc between those 2 points is considered the intercepted arc because it's inside the angle. It's like Pac-Man eating the pills or whatever they call those things. Okay, a polygon is an inscribed polygon when all of its vertices lie on the circle. So what you'll learn in this chapter section is how to use inscribed angles and use inscribed polygons. So let's take a look. Okay, so we have a couple of core concepts to talk about here. Inscribed angle and intercepted arc. An inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle, just like I described in the first page. An arc that lies between two lines, rays, or segments is called an intercepted arc. I've also explained that. If the endpoints of a chord or an arc lie on the sides of an inscribed angle, then the chord or arc is said to subtend the angle. So the intercepted arc, the endpoints of AC, this chord, or arc AC, lie on the sides of the inscribed angle, then the chord or arc are subtend the angle. Okay, so just another fancy word. Now theorem 1010, measure of an inscribed angle theorem. The measure of an inscribed angle is 1/2 the measure of the intercepted arc. Now, there's a proof on page 560, but I'm just going to say it really quick right here. So if you have a circle and I draw an angle and it goes through the center of the circle. Let me just make this flat. Okay, let me put a dot right here. So there's the center of the circle. So the measure of an inscribed angle is 1/2 of its intercepted arc. So this is a diameter. So if I now take a line segment, let's make it red. Let me just put a dot here. What my thing just did. All right, let me try that again. So I'm going to put a point on the circle right here. And if I draw a chord from the ends of the diameter, okay, well, this is 1/2 of a circle, 180 degrees. So what I just did was I put an arc on this, or I put an angle, an inscribed angle from this point on the circle where its endpoints are the ends of the diameter. Well, I know that this is 180 degrees, and therefore this angle is 90. So it's half the intercepted arc, and that's the easiest way to explain it. The arc angle is going to be half of the intercepted arc, and no matter where I move that angle, so if I now move this dot, say right here, and I then move this chord to it, and then move this chord to it like so, and bring that over like that, then this is still a right angle. Okay, so no matter where you are on that circle, this angle, if I move the dot this way, this angle gets smaller and this angle gets larger. If I move it this way, when you're moving away from the angle, it gets smaller and this angle gets bigger. And those two are always going to equal 90 degrees because this is 90 degrees. It's actually kind of neat how that works. So let's take a look at it in some examples. Okay, example 1, using inscribed angles, find the indicated measures. I need to find the measure of angle T. The measure of angle T is right here. Okay, notice point T is on the circle. TS is a chord, and TR is a chord, but it's also a diameter. But it doesn't matter that it's a diameter. All I notice is that this angle right here is an inscribed angle. Its intercepted arc is right here. Let me switch this. Its intercepted arc is right here, 48 degrees. So we have a theorem, since the theorem says the measure of angle T, which is an interior angle, inscribed angle, I mean. And as it says here, the measure of an inscribed angle is 1/2 its intercepted arc. So I'd say the measure of angle T equals 1/2 the measure of arc RS. Okay, so the angle's half the arc. So then you'd say the measure of angle T equals 1/2, and you substitute the given 48 degrees. So the measure of angle T equals 24 degrees. So this is 24 degrees. Okay, and now let's take a look at arc QR. So arc QR, be careful what they're asking for. Arc QR is right here. So let me erase all of this. Now we're looking at just this arc here. But notice we have, let me get my highlighter again. Let's do this. And so here is the key to this problem. This is a diameter. So this is an inscribed angle. So now I can say the measure of angle R equals 1/2 the measure of arc QT. Okay, this angle right here is half of this arc here. Okay, in this case, I know that this is 50 degrees. So 50 degrees is 1/2 the measure of arc QT. So in order to get rid of this half and find the measure of QT, I would multiply both sides by 2. So this 1/2 and 2 become 1. So the measure of angle QT equals 2 times 50. Oops, already had an equal sign. Equals 2 times 50, which is 100 degrees. So this arc right here is 100 degrees. But the key to this problem is this is a diameter right here. And that cuts the circle in half. Okay, so this is a semicircle. So I could say the measure of arc QT plus the measure of arc QR is a half a circle, which is 180 degrees. Okay, so from T all the way around to R, since this is a diameter, this is half a circle or 180 degrees. Or you could think of angle TPR as a straight angle, 180 degrees. And it's a central angle and it equals its intercepted arc. So now I know QT is 100 degrees. And add that to the measure of angle Q or arc QR, and they have to equal 180 degrees. And I subtract that arc from both sides. Then I get the measure of arc QR equals 80 degrees. So this arc right here is 80 degrees because 100 plus 80 is 180. Okay, and that's how you have to like look around and see all the things that you can answer in the circle before even thinking about what to answer. I always like to just fill in the circle with everything I know just by looking at it. Okay, so now let's go on to example 2. Okay, here's example 2, finding the measure of an intercepted arc. Find the measure of arc RS. So let's highlight that so we know what we're looking for. We want the measure of arc RS. That's right there. And the measure of angle STR. The measure of angle STR is right here. Okay, so that's what, and it says, what do you notice about them? Okay, so let's just answer the question first. So I always write a formula. I'll do it over here. The measure of arc RS equals. So since the angle's half the intercepted arc, the arc is twice the angle. So I'm going to say 2 times the measure of angle RUS. So let's highlight that. So here's the angle RUS. RUS intercepts SR, arc SR. So the measure of arc RS is 2 times the measure of angle RUS. Substitute the givens. So the measure of arc RS equals 2 times 31 degrees. So the measure of arc RS equals 62 degrees. So this is 62 degrees. Okay. And once you start seeing this and you see how obvious it is, you just want to just put that 62 over there. But I really would like you to write a formula, substitute the givens and solve, and just get in the habit of doing that. And it may seem tedious and a lot of work, but it'll make your life easier when you go into algebra 2 and pre-calculus. If you can set up an equation like this and you keep doing it and it just becomes routine. Okay, so now we're going to find, so we found the measure of arc RS, that's done. Now we want to find, so now I'm going to say the measure of angle STR equals, well, angle STR is an inscribed angle. So it's 1/2 the intercepted arc, which is also RS. So now I know that STR is half of RS. And then I substitute in my givens. And the measure of angle STR equals 1/2 of 62 degrees. So the measure of angle STR equals 31 degrees. Okay, so let me change to blue here. So this is 31 degrees. So notice what happened here. This intercepted arc RS is being intercepted by 2 inscribed angles, angle STR and angle SUR. So when 2 angles on a circle intercept the same arc, the 2 angles are congruent. And that's what they're saying about what you know. What did you notice about STR and RUS? Okay, so I'm not going to write that. I just said it. If you have 2 inscribed angles sharing the same intercepted arc, the angles are congruent. Okay, so now that I've done example 1 and 2, You should be able to do problems 4, 6, and 8 in your exercises. Okay, theorem 10.11, inscribed angles of a circle theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. So we just did that in that last example. So it's really weird how the book says, oh, well, look what you just did. Here's the theorem that highlights that. So here is angle ADB. And here is angle A, oops, hit the wrong thing up here. Here is angle ACB, and they intercept the same arc AB. So there you go. So therefore, angle ADB is congruent to angle ACB. All righty, so that's what we just verified from the last problem. Okay, this is really easy. So it says, given the measure of angle E is 75 degrees, find the measure of angle F. Okie dokie. So we'll notice something. Angle E intercepts. Oops, I keep doing that. Intercepts arc GH. Okay, see that? The end of chord EG, the end of chord EH intercepts GH arc. Well, then when I look at angle F is right here. And it shares the same intercepted arc. So what I'm going to say is the measure of angle E equals the measure of angle F, because they both intercept arc GH. And the measure of angle E is 75 degrees. So therefore the measure, whoops, substitute the givens, measure of angle E is 75 degrees equals the measure of angle F. Or you could say the measure of angle F equals 75 degrees. Find the measure of angle F, 75 degrees. Okay, pretty simple. All right, now do problem 11 and 12 in your exercises. All right, so now we have a core concept about inscribed polygons. A polygon is inscribed when all of its vertices lie on the circle. So notice what we have here. We have a pentagon, a five-sided figure. This vertex is on the circle. This vertex is on the circle. This one is, this one is, this one is. So when all of the vertices lie on the circle, then the polygon is inscribed. The circle that contains the vertices is a circumscribed circle. So when there's something inside this circle like this, then you say the circle circumscribes the polygon. So it's another word, circumscribed. Okay, so theorems 10, 12. Inscribed right triangle theorem. If a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. And I said that earlier in this chapter to explain why inscribed angles are half the intercepted arc. So what they're saying here is AC is a diameter, and therefore the measure of angle ABC is 90 degrees. So if a right triangle is inscribed in a circle, notice it's inscribed, okay? All three vertices are on the circle. Then the hypotenuse is a diameter. And notice this AC is going through the center. So that is a hypotenuse is a diameter. Okay. Conversely, if one side of an inscribed triangle is a diameter of the circle, so I could move B anywhere around and leave AC where it is, it's a diameter, then the triangle that we create is always a right triangle. Okay, so measure of angle ABC is 90 degrees if and only if AC is a diameter. Theorem 1013, inscribed quadrilateral theorem, says a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Okay, remember what supplementary means? They add up to 180 degrees. So here is angle E. The angle opposite E is G. So the measure of angle E plus G is 180 degrees. It also works for the other angle. If you have angle D opposite angle F, then angle D plus angle F equals 180 degrees. So if these two add up to 180 and these two add up to 180, their sum is 360. And we already know from prior chapters that all four-sided figures, angles, add up to 360 degrees. So all quadrilaterals have a sum of 360 degrees in their angles. Okay, so now let's take a look at some examples. Okay, example 4 is using inscribed polygons. So a triangle is a polygon, poly meaning many, gon meaning side, many sides. Three-sided figure is a polygon. A triangle is a polygon. Triangle ABC is inscribed because all three vertices lie on the circle. So let's use some definitions here. Circle Q circumscribes triangle ABC. Okay. So now it's asking us to find each variable, 2x. Well, 2x is right here. And so I'm actually going to do this. It's a right angle because AB is a diameter. Remember what they said back here, right here. If a right triangle is inscribed, conversely, if one side of an inscribed triangle is a diameter, then the triangle is a right triangle. So AB is a diameter, and that's the side of a triangle, then therefore that's the hypotenuse, and angle C is 90 degrees. So since C is 90 degrees, then I can say 2x equals 90 degrees. Divide both sides by 2, and x equals 45. Okay, so there's x. It's that simple. Say, right triangle, 2x equals 90. Solve. Okay, so now we have a quadrilateral. So remember what they said, opposite angles, okay? Opposite angles are supplementary. So I'm just going to set up two equations right now. The measure of angle D plus the measure of angle F equals 180 degrees. I'm also going to write another one saying G and E are opposite. So the measure of angle G plus the measure of angle E equals 180 degrees. So there's our formulas. And I always say this, geometry is just a bunch of formulas and theorems that set up algebraic equations so we can solve for missing variables. So the measure of angle D, substitute, is Z degrees, plus the measure of angle F is 80 degrees, equals 180 degrees. Solve for Z by subtracting 80, not 88. Solve for Z by subtracting 80 degrees from each side. And 80 minus 80 is 0. 0 plus Z is Z. So Z equals 180 minus 80, or 100 degrees. Okay, same thing over here. The measure of angle G plus the measure of angle E equals 180 because G and E are opposite angles. G is Y degrees. E is 120 degrees. Substitute your givens and do order of operations. Subtraction property of equality, and 120 minus 120 is 0, leaving Y all by itself, and 180 minus 120 is 60 degrees. So angle Z, or I mean variable Z, which is angle D, is 100 degrees, and variable Y, which is angle G, is 60. Okay, so 120 plus 80 plus 60 plus 100 equals 360 degrees. Okay, so now try examples 14 and 16 in your exercises. Okay, so example 5 is a real life situation. So you're using the circumscribed circle in this problem. Your camera has a 90-degree field of vision. Okay, so let's switch to highlighter here. Okay, camera has a 90-degree field of vision. You want to photograph the front of a statue. So in other words, if you were standing right here and it's got a 90-degree field of vision, it can see through its lens over to this corner and this corner of, this is a aerial view of the Statue of Liberty. So it says you stand at a location in which the front of the statue is all that appears in your camera's field of vision as shown. You want to change your location. Where else can you stand so that the front of the statue is all that appears in your camera's field of vision? So what they're saying is if I were to stand over, whoops, forgot to switch to pen. If I were to stand right here, I want my field of vision to still only be the statue. Can that happen? Okay, so that's what this question is asking. So what you need to understand is from this chapter is if you have a 90-degree field of vision, your camera's at this location here, like we were here, and it can see to here and here. Well, if I do a circle and I center it right here, okay, and open it up like so, I'm off by a smidge. Okay, so let me just move it. And let's make it a tad thinner. Okay, so here is a circle. Notice what just happened. We have our camera sitting on the circle. We have a 90-degree field of vision. Okay, so what that means is our hypotenuse, here's the center. Our hypotenuse is a diameter. So no matter where I move my camera on this circle, I am only, if I turn it properly, I'm only going to get the front of the statue, which is from here to here. So basically what they're saying is, if you form a semicircle, no matter where you put that camera on that semicircle and turn the camera so that you have the edge focused view to here and here, you can be anywhere on this semicircle. And that's the answer to this question. So anywhere on this semicircle, you can put the camera and rotate it so that you only get corner to corner of the front of the statue. And that's all there is to it. So now answer exercise 18. Okay, so that brings us to the end of chapter 10.4. Please do these problems in your exercises. Thanks for watching and have a great day.